number 6. During a certain epidemic, the number of people that are infected at a particular time is proportional to the number of people that are infected at that time. We have 1,000 people that are infected at the very beginning. 1,200 7 days later. How many are infected 12 days after the epidemic is first discovered? So this is back to dp dt is directly proportional, so we can use this equation. Since they told us the initial value, we also know what our c value is. So this will be P equals 1,000 e to the kt. And let's go ahead and solve for k by using our next values, and that's when we were 7 days later. So 7 days later, we had 1,200. We're solving for k here. You can see we can divide by 1,000. Then take our natural log. So therefore, k equals the natural log of 1.2 divided by 7. Okay. That gives us a new equation of p equals 1,000 e to the natural log of 1.2 divided by 7 times t. And yes, I'm going to write it that way rather than get some decimal here and then truncate that and then be off in the end. Okay? The decimal places are pretty important when we do these types of problems. Okay? Now, I think we're ready to find p of 12. Just a matter of using a calculator correctly. This will be an e natural log of 1.2. In the right spot, divided by 7 times 12. We put that in our calculator correctly, we should get 1,366.907, or typically we would probably round that. If it said round to the nearest or to the number of people, we haven't reached that next person, so that would be an acceptable answer for this one. Let's take a look at number 7. It says the weight of the population of yeast is given by a differential equation. And they give us the differential equation. Sure looks like the ones we've been talking about again. They give us an initial condition, and they say it is increasing at this particular rate. Okay? So, based upon what we have, y sub 0, initial condition gives us 120. So based upon that, we know that C is going to have to be 120. Okay? And then we can actually solve for y because they give us dy dt. Okay? So let's go ahead and substitute those in. We know when t equaled 0, we had a population of 120, and we're given that the rate of change was 24. So 24 equals k times that 120 that we had, or k would equal 24 divided by 120, which simplifies to 1/5. So our equation for this will be y equals C value, remember we're just jumping to this one, of 120, e to the k, we just solved for k over here, 1/5 times t. Pretty simple and straightforward problem to do. Let's take a look at number 8. It says, during optimal conditions, the rate of change of the population of a certain organism is proportional to the population. So again, we're back to dp dt equals k times p. We have some initial conditions also on this one to consider, so let's take a look at that. And this one is saying, what is the population, or at what time? This one's looking for a time this time, that's why we're doing this one. What is the time when our population equals 500? P of what equals 500? All right, so You can see initial conditions, P equals 300 e to the kt. We're given a value at 24. We'll use that to solve for k. 1,000 equals 300 e to the k, to the k times 24. Almost wrote t there. And we can divide both sides by 300. 1,000 divided by 300 equals e to the 24k. Take the natural log, and of course I could probably simplify that to 10 thirds equals 24 times k. That means k will equal the natural log of 10 thirds divided by 24. That means our differential equation, our equation for this population will be P equals 300 E, now that we know K, natural log of 10 thirds, all divided by 24 times T. Now let's solve this one. Substitute in 500 equals 300 E to that mess, natural log of 10 thirds divided by 24 times the t that we're looking for. Okay, let's go ahead and, in this case, we're dividing both sides by 300. I'm going to jump a couple steps here. I know that I'm going to also natural log that. 500 divided by 300 is 5 thirds. That's going to bring all of this mess down to the natural log of, when I take the natural log of 10 thirds divided by 24 times t. T then will equal, I'm going to multiply both sides by 24, 24 times the natural log of 5 thirds, all divided by the natural log of 10 thirds. And that's what time that is. If it were a calculator, we would put it in our calculator. If it's a non-calculator, we're just going to leave it like that and put our units of hours on that. Let's take a look at our next one. It says during a chemical reaction, the rate of change of the amount of chemical remaining is proportional to the amount remaining. So again, we're back to that good old dm dt equals k times n, initial amount, a given amount, and just a matter of substituting in. We know that this will be the initial value of 12 e to the kt. We'll use this for moles. Sorry, let me check my numbers there. Yep, at time t equals 4. So this is 12 e to the k times 4. When I divide by 12, this should give me 1/3 e to the k times 4. Next, I'll take the natural log. The natural log of 1/3 should equal k times 4, or 4k, which means k equals the natural log of 1/3 divided by 4. We're going to check this out, we'll first put this in our equation. 12e, our k value, natural log of 1/3 divided by 4 times t. Then substitute in 3, m equals 12e, natural log of 1/3 divided by 4 times 3, whatever that is. Again, if this is without a calculator, we'll leave it like that. And this, of course, was in moles.